Zero credits to earn. I'm like, are you selling this?
I got today, tomorrow, so basically it's like an finish that. All those things need to go. Yeah, I have a good idea of what I can do. That's why I have,
Alright, everyone. Alright, so Tristan is sick, or not sick. Terry is sick today, and Tristan's out of town, so Cam is stuck with me introducing him. So, it is my honor to introduce Cam, and I'm excited to see what he has in store for us today. A little background on Cam. He graduated from Cornell in 2020, majoring in atmospheric sciences. Fun fact, he was a marine biology major up until his junior year, which I did not know. And then he started his master's here at UW, where I've enjoyed the opportunity to get to know him through class, even with COVID and everything being online. But I'm excited to learn more about him as we finish our PhDs. So research interests. At the moment, he's still unsure exactly what his research interests are, but he likes the interdisciplinary nature of the field and being able to dip his toes on a lot of different topics. He enjoys algorithm development and using computational methods to solve problems. His hobbies are he rode in college and enjoys endurance sports. I know he just ran a marathon, which is amazing. And he also likes hiking and eating. So the title of his talk today is Characterizing Bimodality, sorry, I cannot talk today, an ensemble forecast of 2-meter temperature. All right, so take it away, Jim.
Yeah, thank you. Is this volume good? Okay, yeah, so I'm going to be talking a little bit about some research I started in undergraduate that I try to continue whenever I get some extra free time here. And it's surrounding looking at these bimodal distributions that occur in these ensemble forecasts. And so I want to start, though, by saying I haven't done this project alone. Peter Hitchcock funded me to start this project after my junior year, and then Art and Rewall both have helped a lot in terms of helping, suggest future directions for analysis, and then offer edits to papers and stuff like that. So I'm going to start by just giving a very broad overview of ensemble forecasts for maybe those who aren't super familiar, as well as giving some motivations for the study. So ensemble forecasts are essentially just a group of forecasts that are perturbed relative to one another in some way. And so that might come in the form of different perturbations to the parameterization, so assumptions that go into model physics for each of the members, or perturbations to the initial conditions, which is what is the type of ensembles we'll be looking at for this study. So because of the chaotic nature of the atmosphere, even small perturbations will ultimately lead to spread over time in the ensemble. So you can see that in this little cartoon here, where initially you begin tightly clustered around some single state in the phase space, and then as the forecast lead time extends, that ensemble spreads relative to one another. And so quite commonly, these forecasts might be treated as Gaussian in the sense that you might use the mean of that ensemble to represent some most likely future state of the atmosphere at a given time, or you might use the spread of that ensemble to represent some amount of uncertainty associated with that forecast. And so going off that cartoon here, here's a representation of a real ensemble for a 2-meter temperature. It's a 50-member ensemble. I plotted each of the ensemble members' evolution in the thin gray lines, the ensemble mean in the thick black line, and the dashed lines is just assumed deviation surrounding that mean. And then finally, the yellow line is the observation values. So you can see, as we saw in the little cartoon, initially the ensemble remains, relatively tightly clustered together for the beginning parts of the forecast lead time, and then after roughly 30 days or so in this case, there's some larger amount of spread. And so commonly through this presentation, I'll use these kind of like contour plots to represent just a continuous form of this ensemble. So essentially, you can just interpret it as darker shades of red mean more ensemble forecasts predict near that temperature. Lighter shades of blue mean less of the ensemble members predicted near that temperature. And this just makes it a little bit easier to see what's going on. So here now is a set of two different ensemble forecasts. I'll point out it's for the same location, just two different initialization dates. So we'll look at the top one first. And you'll see even after 30 days, in this case, there's actually not that much spread amongst the ensemble. And I can take, a cross-section through any one of these given lead times and plot what the ensemble distribution actually looks like. So on the x-axis here, I plotted the discrete values that each of the ensemble members are predicting, and I'll fit both a non-Gaussian and a Gaussian fit to that distribution. And for argument's sake, I'll say they're relatively similar in this case. So, maybe there's some slight differences, but for the most part, there's some kind of clustering around a temperature of zero, and then some spread surrounding that temperature. And I think you can see that's probably the case for a lot of the lead times for this particular forecast. But then you can look at this bottom one and see that's most definitely not the case for a lot of these times. So again, I'll just take a cross-section through any one of these forecast lead times, in this case around 6 days, and you can see the Gaussian fit and the non-Gaussian fit differ by quite a bit more in this case. And so it seems like there's kind of this preferential behavior for the ensemble members to be attracted near this temperature 0 degrees C, negative 10 degrees C, and maybe several lines some in between temperature. And so I'll also point out that where our Gaussian fits a maximum probability lies very close to relative minimum probability for a non-Gaussian fit. So the distributions differ by quite a bit more. And I think you can see that happens probably in a lot of these cases for this particular forecast. And it actually seems like the observation values kind of seemingly bounce around in between these two modes in this case. And so beyond kind of this operational implications of assigning very different probabilities to this same set of ensemble members, there's this interesting kind of behavior of being attracted to these two very different states with not so much something in between. And so we really wanted to start to explore, okay, does this happen frequently? Where and when does it occur? How poor may Gaussian perform in their presence? So you can imagine as those two modes kind of separate further and further apart, that dip in between might get deeper, and using the mean of the ensemble becomes an increasingly poor assumption. And then finally, what's actually causing it to happen? And so I split this presentation up into two parts. The first one kind of concerned with tackling this where and when, and then the latter part being maybe the more difficult question of what's actually causing it. So, of course, as with anything, this wasn't as simple as I thought it was going to originally be. And that's because of this kind of limited sampling problem associated with these ensemble forecasts, where because our ensembles are just discrete points of what we hope to be the true evolution of the atmosphere, we can get these kind of misrepresentations as a function of our limited ensemble sample size. And so I think this is a bit easier to see through this kind of synthetic sample that I've generated, where, say, our atmosphere is attracted to the single state, and there's some spread surrounding that state. So that would be representative of the black distribution. And we can draw two different ensembles from this distribution. So, here's an example of one ensemble forecast with the blue tick marks, where there's 10 members just randomly sampling 10 points from that black distribution, versus another ensemble, the red tick marks, where again I just randomly sampled 10 points from that distribution. In the first case, our 10 members do a pretty good job representing this distribution. The blue distribution and the black one are pretty similar. But then, kind of by chance, I happen to draw more on the right side, more on the left side for the red ensemble, and I fit a distribution to that ensemble, and I happen to get something that's bimodal, even though we very clearly see we're not drawing from a bimodal distribution. And so we needed a way in which we were disentangling kind of this bimodal frequency in these ensembles as a result of just this limited sampling problem, or because the atmosphere is actually being attracted to these two very different states. And so I tackled that through these and a lot of the discussion that I'll continue with is surrounding these kind of 4 statistical definitions. So this is a bit of a slog, but bear with me. The first being this idea of a kernel density estimate, or KDE, which is just representing a non-Gaussian way to fit to the ensemble. So prior I was saying non-Gaussian fit. In reality, it was this KDE. And so you can look at this little cartoon here to see what that actually looks like. It's basically just the superposition of a bunch of Gaussian distributions on top of each other. And so that's like, so the KDE fit to this ensemble would be the blue curve. And then the second definition I'll say is delta, which is just for a bimodal distribution going to be the spacing between the two modes that are generated. So in this case, we have one mode maybe centered around -1, one mode maybe centered around 6, and so I'll say the delta of this distribution is 7. And then our final 2 definitions we make up for the purpose of this study. This first one being the idea of this mode probability ratio, which is essentially just describing the probability of our peak in our distributions relative to that of our minimum that lie in between. So we can look at this purple one, the peak on the left, for example. It's got a probability of roughly 0.14. The minimum that lies in between them is roughly 0.07, so we say, oh, this mode probability ratio is 2. And so the deeper that difference is, the more extreme, or the greater value of our mode probability ratio. And so since every bimodal distribution has 2 peaks, they'll have 2 mode probability ratios. And then this final definition now is this idea of membership, which is just going to be how many members reside in each mode of our bimodal distribution. We choose to assign that solely as a function of where they lie relative to our KDE's minimum. So, if they lie to the left of it, they're assigned mode 1. If they lie to the right of it, they're assigned mode 2, and we kind of move on. So, using these 2 previous definitions, we choose to add some restrictions on what we consider bimodal in order to make kind of like a more robust definition in order to deal with this kind of limited sampling problem. So the numbers aren't super important. It's more so just that we do this and then you'll see the result. But we add some minimum threshold to our mode probability ratio and some minimum threshold that has to be satisfied in our membership. So again, for the sake of time, I'm going to be relatively brief in describing how we derive these 2 magic numbers. But it comes down to, we generated a bunch of distributions that we knew to be unimodal, a bunch of distributions that we knew to be bimodal, and then we can repeatedly draw 50-member ensembles from that and see, okay, how often is it assigned bimodal when we know it's truly unimodal, or vice versa. And then we can impose all the different combinations of the mode probability ratio requirement or the membership requirement to try to minimize like the false positive identification of what we know to be unimodal distribution. And so I'll ask you to trust me when I say we test this with a bunch of different unimodal distributions, these requirements that I listed, and we find approximately a 5% false positive identification due to this like limited sampling issue. And so if we find anything more than that though, we'll say, okay, this might be actually caused by, the atmosphere truly being attracted to these two different states. So after all this, we're finally able to apply this to real data. So we use the ECMWF ENS-extended forecast, and we're focusing just on 2-meter temperature. These are 46-day forecasts. They're 6 hourly, initialized every Monday and Thursday, and they're 50-member ensembles. And so the forecast set that we have extends from the 3rd of December 2015 until 28th of January 2021. So we got roughly 550 forecasts to work with, so we can get at least a nice bit of samples to test on. And so I'll first focus just on this left set of panels, and I bend this into 3 different kind of groups of lead times based on when our forecasts are valid. So, for example, the top left is saying, okay, for all the forecast lead times that are in the first week, how frequently are forecasts bimodal according to our KDD? And I just white out everything that's below that 5% threshold that we saw. And then, weeks 2 and 3 are in the middle. And then towards the end of our forecast, lead times, weeks 4 and 5 are the final panel. And so I'm not going to focus too much on this slide for the regional patterns, because I have some blown up figures that's easier to see. But I'll point out first, kind of irrespective of the forecast lead times we see over much of the globe, it's well exceeded by this 5% threshold we've set. And like in some places you're getting 30% of forecasts are bimodal, which is absolutely ridiculous. And then, let's see, as a function of lead time, it seems like generally the bimodality frequency increases, which is kind of consistent with this idea that it takes time for ensemble members to spread apart from one another. So, it won't happen immediately. That being said, though, it does seem like there's kind of a maximum that occurs during weeks 2 and 3 versus some slight decrease maybe into weeks 4 and 5. And that might be due to like these forecasts starting to lose some amount of skill. And so you just kind of get like approach to climatology where you get some kind of uniform spread and it reduces the bimodality frequency. And so then I'll look at the right side. And so this is for those forecasts that are bimodal. What's the delta and the mode probability ratio for those distributions? And so I'm going to talk mostly about delta, but again, perhaps not super surprising. As a function of lead time, the delta seems to increase, and that's just, forecasts can spread out further from, or the modes can spread out further from one another. What's up?
What's the season that your experiment is in?
This is for all forecasts initialized, irrespective of the time of the year.
Okay.
But that brings up, this part, I've now isolated as a function of season. So I focus now on just weeks 2 and 3, because that's where our maximum occurrences were occurring. And I want to see, okay, can we see this kind of seasonal dependence? And so here I isolate to only this forecast initialized during Northern Hemisphere extended winter, and here Northern Hemisphere extended summer. And so I'm going to flip back and forth a few times so you guys can look at what you see. You can see my bad PowerPoint editing skills if they don't line up exactly. So again, for the sake of time, there's a bunch of really interesting regional kind of characteristics that are occurring. I'm just going to touch on kind of the few big things that I saw. First, so there's very clearly a seasonal dependence where these frequencies as well as the deltas seem to be greater for the winter hemisphere. Secondly, it seems like the occurrence rates are typically larger over the ocean compared to that of the land. But that being said, the delta values associated with those bimodal forecasts seem to be greater over land compared to the ocean. what else? We can look at the tropics specifically, for example, and see kind of irrespective of the time of year, this maximum bimodality kind of persists. And we can even go back to here and see the tropics are kind of unique because, you know, it surpasses this 15% threshold or whatever, even early into the forecast lead times. And so, you know, we can start to make inferences here just based on the regional patterns and say, oh, we know convection works on really fast timescales. Perhaps that's the reason as to why it develops so quickly. We can see over the Gulf Stream, there's this persistent maximum, and that might be with, there's some forcing caused by the SST gradients. The polar regions are somewhat unique because, like, oh, I can use this. You've got here that's having this kind of persistent maximum, and then basically the entire Southern Ocean has this persistent maximum. And even though it's over the ocean, we're getting really incredibly large delta values for those distributions. And so, you know, that might be something unique to the polar regions, perhaps having to do with interaction with sea ice or something like that. Yeah, I guess that's all I'll say for this. Anything someone wants to point out? What's that?
I guess I'll just point out, especially at 60 South in DJ, I see jet dynamics coming into play and where the strength from there is located. As you're switching between seasons, you can see the jets moving in that pattern switching.
Yeah, so, yeah, good catch. So it seems like there's definitely some kind of baroclinic forcing of some sort where, and like especially we see, you know, this dependence on delta in the winter season where larger temperature gradients, if there's some dynamical forcing, you know, we're advecting, we have some much larger meridional gradient in temperature, so we can see how those modes depart by some greater amount. Okay, so moving on to part 2, this seems to very obviously be happening a lot. So we wanted to start to explore, can we explain it in some more rigorous way than just saying, oh, we see these kind of regional patterns and seasonal dependence. And so the way in which we try to do this is using this clustering methodology. And so maybe for those who aren't familiar, clustering is essentially a way in which you can group points together based on some metric to create these groups or clusters. And so we can look at this animation for, you know, these points distributed in some XY plane or something, and say, okay, maybe we want to group these points based on some spatial distance relative to one another. And so in this case, 3 clusters being made, and you see there's some kind of optimization routine being run to form some optimal set of clusters where the green is one cluster, blue is one, and red is one. And so we wanted to try to do something similar to see, you know, we've got some univariate identification of this bimodality in the sense that we've said, okay, this distribution is bimodal, this one's not. And so we wanted to see if there is some kind of dynamical forcing to create this bimodality. It should have some spatial and temporal coherence, possibly. But we wanted to see if we could see this without explicitly having to force that in the clustering routine. So we wanted to make this clustering routine not a function at all of space or time, but rather something else. And so what we chose to do was this idea of clustering based on this ensemble grouping behavior, where if you remember back to our idea of membership, we chose to assign members to belong to one mode or the other based on where they lie relative to the minimum. And so our thought process was, okay, if these dynamical events are causing these modes to develop, those modes should develop based on the unique initial conditions that are applied to our ensemble members. And so by the same event affecting the same, by the same event affecting the members the same, this kind of preferential grouping should occur for all those forecasts which are being hit by the same event. And so this is kind of an abstract idea, and so I've tried to plot some examples to help solidify it. But first, we can look at this example forecast, which say this is a bimodal forecast of a 5-member ensemble. Ensemble member 1, 4, and 5 are in the left mode. Ensemble members 2 and 3 are in the right mode. And so we just kind of make some like binary vector form of this ensemble where if the member resides in the left mode, it's assigned to 0. If it resides in the right mode, it's assigned to 1. And so here's an example maybe of 2 forecasts that might be grouped together based on this clustering routine, where we can see these forecasts, the fit distribution doesn't necessarily look exactly the same. It's got slightly different shapes. It's not even centered around the same temperature, but because ensemble members 1, 4, and 5 are in the left mode, and ensemble members 2 and 3 are in the right mode, they've got the same kind of binary vector, and this distance formula is going to be evaluated as 0, and so they're very close to one another in this kind of phase space. And so here's an example of 2 forecasts that probably aren't going to be grouped together, where they've also got some unique location in space and time, and they look like they have the exact same shape, and they're centered on the exact same temperature, but their ensemble members reside in different modes in this case, and so that causes their membership vectors to have to look very different, and so you get some distance function that's much greater than 0. And so again, this clustering routine is not at all dependent on the time or the location of the forecast. So, in this case, maybe the forecasts are right next to each other, and they occur right next to each other as a function of lead time. But because they don't look the same in their forecast distribution, they probably won't be grouped together. And there's not even a dependence on the absolute temperature of those distributions. And so, kind of one final note before I show these results is, unfortunately, clustering can be computationally expensive. So you can imagine we have to make kind of these distances for all of our forecasts that are bimodal, and in some of these cases we're getting ridiculous occurrence rates. So there's going to be a lot of them. And so we limit this clustering routine to be performed on a few select conditions. So first, we only focus on those forecasts which are bimodal during weeks 2 and 3 of lead times, because that's where maximum occurrence rates were. And then we also focus on these 3 particular regions, one in the North Atlantic, one over South America, and then one in the Southern Ocean. And so I'm going to plot now an example cluster that's formed from this routine. So I'll just let this keep looping through, but I'm choosing one of our regions, so the Southern Ocean region. I'm picking one of our forecast initialization dates, where we have 538 forecasts which we're letting this routine run on. And then I'm just plotting one of the forecasts, the clusters that are formed. And so all I'm saying is, run me through all the different lead times within this region, and if it's assigned to cluster X, plot a point for that lead time. And I think you can very clearly see, this particular cluster, so these bimodal forecasts are clustered together in space and have some relationship in time in the sense that, we're not getting random blue X points occurring right now, or right now, or right now. They're moving in from the west whenever they move in. And it seems like they grow in occupancy, so there's more blue X's occurring, and then it starts to shrink, and then eventually it disappears. What's up?
Just a quick question. So, just to clarify,
being a part of the same cluster doesn't mean a particular mode. It means a particular similarity between its two modes. Thanks.
Yeah. Okay, so we see this kind of spatial and temporal coherence in this particular cluster without, when we said we didn't explicitly force this to happen. This is solely a function of that kind of ensemble grouping behavior. And again, I'll ask you to trust me, we evaluate this kind of in some more systematic way, and we find this to occur for a lot of the clusters we look at. And so it seems like, you know, they're tightly grouped in space, there's some kind of grow in occupancy, it reaches some peak in size and then decreases in size. And so, you know, that might be representative of these kind of dynamical events maturing in the region, reaching some peak in evolution and deforming, and causing this bimodality to occur. And so we then create this kind of more rigorous definition of a bimodal event where it's just saying, okay, we want to look at only like these large bimodal forecast outbreaks where, you know, just give me, we're just limiting our analysis to all those clusters which satisfy some 85th percentile in occupancy. So we're only looking at these clusters that are really large. Again, we kind of arbitrarily pick this 85th percentile threshold. And so now, that previous event that I showed happened to qualify for that threshold, and so, you know, it'd be qualified as a bimodal event. And we can actually characterize these events based on some of their properties. So we choose to fit an ellipse to the cluster. So you can see that here. And we can use that ellipse, for example, to help try to understand what event is what dynamical events actually causing this to develop. So, you know, we might use the persistence of the cluster, for example, to say, okay, this event lasts for X days. We might use the spatial area of that fit ellipse to say the event's affecting such and such area. We can use the velocity of that event to see its direction of propagation and its phase and its speed, and so on. And so I'm going to focus now on just looking at this South America region. And here's just an example for, I've plotted for all our bimodal events, show me what the, on top, the average event length is, or the distribution of event length, event area according to that fit ellipse, and then the event's velocity. And I separate for the bimodal events that occur during the cold season and during the warm season. And so you can see, you know, the typical event, for example, in the cold season lasts for 2 days, slightly longer than the typical bimodal event in the warm season, which is a day and a half. The typical cold event is much larger than the typical warm event, and it propagates west to east through this region at a speed of, you know, 10 to 15 meters per second or whatever. And so then we can also look at, okay, where do these bimodal events actually most frequently occur within the region? And so I plotted basically an event, a spatial density map here where darker shades of, the darker shades indicate where the events occur more frequently. And then I've also plotted some individual tracks of these events. So, like for example, the white triangles say where one track begins, and you can follow the line and it devolves and ends at the red triangle. And so these tracks that I've plotted are heavily thinned from the total amount of events that actually occur within the region. And so we chose to focus on this kind of really deep maximum that occurs just to the east of the Andes during the cold season. And we wanted to try to understand what's actually causing that. Because that seems like it's, you know, a large portion of the bimodal kind of outbreaks that are occurring in this region. And so the final piece of the puzzle to this was this use of the cluster as meteoroid, which we'll just say is like kind of like the most representative point of that cluster. So, you know, in the case of our little animation cartoon, these little stars might be the cluster's meteoroid, whereas some center of it. And so in our case, though, however, our meteoroid is just going to be whichever of those binary ensembles occurs most frequently within that cluster. And so we can use that meteoroid now to plot how, for a bimodal event, how one of our modes develops versus our other mode. And so I'm going to plot for one of our particular bimodal events that we saw cause this, that one of our particular bimodal events that occurred where we had this outbreak just to the east of the Andes. I'm going to say, okay, give me the meteoroid of that event. I'm going to plot mode 1's evolution versus the second mode's evolution, just to see, what's actually causing this to happen. So the bottom plot is probably easier to see what's happening because it's the difference between the two. So you can see, I'll let it play through one more time. So you can see there's this really large departure that occurs after 10 days or something, where all of a sudden there's this kind of rush of cold air that occurs in, relatively cold air that occurs in mode 1 versus that of mode 2. And you can see, oh sorry, I probably should have explained. I'm plotting the 2-meter temperature field as well as I think it's the 10-meter wind vectors. So you can see it's also accompanied by these comparatively much greater southerly flow that occurs in mode 1. And so we find this to be the character of these cold air incursion events, which are relatively well documented. So Garrod made this kind of climatology of these cold air incursion events in the South America region. And I choose to just, from that previous bimodal event, take a snapshot through one of our lead times. And I plot as well as, I plot on top of that the geopotential, or geopotential height field. And so you can see our geopotential height field for mode 1 almost exactly matches that to this climatology of cold air incursion events. And so it's really cool to see that, this specific bimodal outbreak can be actually connected to some physical dynamical event that's well reported to occur within this region. And it also is documented to occur relatively frequently, so that helps explain, these large occurrence rates. If this happened once in a blue moon, we're not going to get the 30% bimodal occurrence rates that we see. And so I'm not going to go into the dynamics because I probably can't explain them very well, but essentially it seems like some atmospheric wave passes through, the high interacts, kind of wraps around the Andes, and it causes some sort of blocking event, which causes this rush of southerly flow, and accompanied with it much colder air, which, as you saw, happened in our animation. And then I'm finally going to go through I'll go through the abridged version of the Southern Ocean region. Again, same process, just for a different region. We see the average event length is 2.5 days. Slightly shorter events occur during the warm season on average. But again, the average event is larger in the cold season than the warm season. These events typically propagate west to east and at slightly slower velocities than our previous region, 5 to 10 meters per second in this case. So kind of very different behavior depending on when the event occurs. So for the cold season, it's kind of this, most of the tracks just progress west to east over the Antarctic Peninsula. But then during the warm season, there's this kind of interesting behavior where it's like almost some bleeding out from the continental edge. And so, again, I'll use our meteoroid for one given bimodal event and plot the differences between the two modes. And you can see from the wind field, it seems like some atmospheric waves propagating through the region, where to the east you get some anomalous or some relative northerly flow. To the west of that wave, you get some relative southerly flow, and you get these extreme departures in temperature occurring based on where they're oriented relative to the wave. And so I'm not sure I'm ready to buy yet what's actually causing this to happen. So for this region, for example, for all the bimodal events that occur within the region, I plot, okay, what's the average temperature for the warm mode? What's the average temperature for the cold mode? And that's plotted here. And it's a function of all of our different forecasts that we have. And so you can see there's this far less spread associated with our warm mode compared to that of our cold mode. And I think that's consistent with this idea that these events are largely due to like some sea ice forcing, as I hinted at the beginning, where, you know, in our warm mode, for example, there's no sea ice maybe, and the ocean can flux heat at some regulate, you know, kind of variability irrespective of the time of the year. So you don't see much spread in that red distribution. But in the other mode, you know, perhaps there's no sea ice there, and there's going to be much more variability in what that temperature actually is based on the specific atmospheric state at that time. So you get some much larger spread, and you can kind of see this like seasonal cycle occurring as a function of, you know, the cold mode's average temperature. And so yeah, I'm not sure I'm ready to buy yet whether this is representing, you know, some influence on the sea ice field itself by the low-level winds, you know, advecting sea ice around, and, you know, sea ice gets pushed over some region in one mode versus not pushed over that region in the cold mode, or in the warm mode, then it's much different. Or if it's solely as a function of like advection across the sea ice. So you can imagine like along the sea ice margin, if you've got the wind field going from ice to ocean, it's going to have a very different temperature associated with it than ocean to ice. Or maybe it's some combination of both, but I'm not really sure with this one yet which of those it exactly is, but I think it's relatively clear it's some interaction with the sea ice. And so, summarizing here, you know, we've identified that there's this really frequent attraction to these preferential states and these ensemble forecasts, and we know the assumption of Gaussianity performs really bad in their presence because there's, in a lot of these cases, insanely large separations between the two modes. And so we find this most frequently occurs in weeks 2 and 3. It's more common over the ocean. There's larger mode separation over land, though, more frequent in the winter hemisphere, and yada yada. There's a lot of really interesting kind of regional aspects to this. And so for all 3 regions that we looked at, however, it seems like there's this kind of common denominator of this interaction about these atmospheric waves that propagate with the region, through the region, and how they interact with like local processes, whether that be topography, you know, the sea ice field, or what we're kind of finding with the North Atlantic region. It's the interaction with SST gradients in the Gulf Stream, and causing like, we think it's associated with causing like Rossby wave breaking events and stuff like that. And so for future work, if I were able to keep doing stuff with this, you know, we've kind of lived and resided in model world for this whole time, but it's probably important to actually see, you know, what is the true geopotential height field looking at for these times that we're predicting? You know, is it actually attracted towards one of these 2 modes, or, you know, is this a model artifact? And it's really not exactly clear to me yet. I think would be an interesting study is why, you know, while these mechanisms make sense as to cause these extreme departures. So like, you know, for example, the advection over the sea ice, it's really easy to understand, you know, ice to ocean versus ocean to ice can cause these extreme departures. but why is it something like total opposites like that rather than just some spread in between those two situations? There's something to do with, how these forecasts are initialized and the initial conditions that creates like some kind of cutoff point that makes them to be attracted towards these two different modes. And then, I made kind of a lot of assumptions and stuff like that in this question routine, or I think if I actually wanted to use this to identify new regimes or identify ways in which some stable atmospheric state might transition to a different regime or something, it probably needs to be optimized in some way to like make it more robust to that or something like that. And then so far I've only focused on 2-meter temperature. I think it's a nice variable because it encompasses a lot of different fields. It's going to be affected by advection, radiation stuff, the boundary conditions, yada yada. But it's probably worth seeing what develops in these different atmospheric variables. So that's all I have. Yes.
Is this a coupled model? And does it have, it actually has the pricing?
Yeah, so that's a good question. And so Peter Hitchcock, who has been kind of my advisor through this, he, I think, has connections at ECMWF and stuff, and I was like, after talking with James some, I was like, okay, it's probably worth seeing if like that's even possible to like eject the sea ice field, like will that actually occur? And he forwarded me back the email from someone who works on the model, and both of us were like, I didn't really understand what she just said. So it seems like that is possible in this ECMWF model, but it changed in 2016, which is like we have 1 year data prior to that and then 4 years after that. So I think I can go back and see if the behavior of these bimodal events differed, whether they occurred prior to that date or not, to help unravel that. But yes, it is possible. I'll go back to front. Liz.
Forget maybe you showed this. If you take a look at the first day when modality starts to appear, and I ask because perhaps what you're seeing is the breakdown in weather predictability around age 14 days. This is a representation of that 2 weeks past heading out into some time scale.
Sorry, wait. What I didn't. What was the first part of the question?
The question is, what day do you first start to see bimodality? Day 8, day 15, day 15?
Yeah, so I did just this like rough binning procedure, so I haven't done like day 8. It reaches a maximum or whatever. But what I did do is I wanted to see if, so in regards to your question of, is this just starting to be the breakdown of the weather predictability and the forecast is starting to lose their skill? I looking at even the longest lead time, so even days 40 to 46. Do those distributions approach the climatology? Because I figure if that distribution's at climatology, the forecast essentially has lost its skill, right? And we find that's not the case. Even at these ridiculously long time scales, it has some uniqueness based on when the forecast was initialized in the atmospheric state at that time. Did that at all answer your question or no?
Yeah, pretty close.
Okay.
Really cool, by the way. This is a really neat analysis.
Thank you. Yeah.
So I was kind of curious about the thought process behind 2-meter temperature. The reason for that is I'm thinking about the and 2-meter in most numerical models that I understand is that you can extrapolate this quantity coming out of mononova similarity theory, which has switches in it as a function of stability. So curious, is there some bimodality occurring just because of the boundary parameterization kind of switching between these states. Whereas if you look at something like 850 millibar, you kind of get away from some of that additional source of uncertainty.
So I think the reason I was assigned to meter temperature was because I. What?
Fine, that's a good temperature.
Yeah. Well, no, I think I started this probably when I knew nothing about nothing, and I'm sure Peter was trying to be nice to me and say, 2 meter temperature, that makes the most sense to you. Try this. But, so, I mean, a lot of what you said kind of went over my head, honestly. But I think maybe this will help answer that question is, I did try to see, you know, if this is a function, so if this is a function of different model parameterization, for example, we would expect the members to preferentially group into 2 different modes, irrespective of when the forecast is initialized or not. And so I tested, you know, for all forecasts that are bimodal, take some, you know, tracking member, so ensemble member 1. If it was a function of the model parameterizations, you know, the other members that are parameterized similarly should preferentially group with that across all forecasts. And we found that to not be the case. So, you know, it's essentially random in terms of whether it groups, which members group with which, if we just average over all the bimodal forecasts. Would that maybe address that?
I think so. I gotta think about it, but I love your message. I think it could be applied to a lot of different types of problems. So,
Go ahead, Jane.
Okay. The southern air, cold air incursion, that got me thinking, is it that there's 2 modes, or is it that there's like normal climatology and like some crazy event that there?
So yeah, it's interesting because, you know, one of the contexts we've thought of applying this to is this idea of like transition between atmospheric regimes where, you know, maybe there's some stable state of the atmosphere, and for whatever reason, you know, how you initialize the model, it might cause this transition to a different regime, and that could be expressed as some bifurcation behavior in the model. And so I think in some cases it is just like there's zonal flow in one mode, and in the other mode, you know, you get this atmospheric wave propagating through the region. And there's other cases though, you know, for the Andes region, for example, where like the waves are just at different stages in their lifetime. So, you know, both times they're being predicted, it's just they're shifted a phase or half a phase or something like that, and it causes this, you know, very different temperature advection field based on where that's situated relative to the Andes.
And sorry if I missed this, from class. Did you look at instead of looking at forecast ensembles, did you just look at a climatology bimodality? Did you do that?
So are you asking like, oh, maybe this is just approaching the climatology, which in itself is bimodal?
Yeah.
Yeah, so I think we kind of tried to kill, so that is not the case, and we found that partly because we, you know, in the same thing that I said to address Liz's question, we found that these forecasts weren't approaching the climatology even at the longest lead times.
What do you mean by they aren't?
Earths aren't at the climatology even at the longest lead time. So for example, like we can look at, so we can generate some climatology for distribution, and we can average all of our forecast distributions that occur in days 40 to 46 or whatever. And we can compare those like through a KS test or something like that to see if they're the same. And we found that not to be the case.
So kind of the forecast distribution cannot approach the climatological
Mhm.
factor. Okay.
Yeah.
The thing I guess I'm wondering is, you know, you're seeing this right next to gradients. The 2 things I'm wondering. You're seeing this show up next to where there are large gradients. Where you know, if you got a large gradient, then you go one direction, you'll see a big change, the other direction, you no change. So you get bimodality out of that. But it's being near a gradient.
Yeah.
And then the other one is with the initialization of the forecast. I don't know whether they initialize with as too much, I don't know whether that's whether they're initialized singular vectors, or do you know that?
I think they are. I think so, yeah.
So anyway,
All right. Yeah, I'll take that into consideration. Thank you.
It's an online question.
Okay, sure,
Judge.
yeah.
Stephanie Bradshaw asks, since you completed this work, do you anticipate any improvements that could be made to reduce the computational expense nature of the methods you've discussed?
So I'm sure there's ways in which you can speed up the computational time for the question routine. But I do think, where at first we found this limitation to having to limit it to these regions being perhaps limitation. Because we found a lot of these to be this large-scale interaction with local processes, I actually don't think it's that big of a deal, where we're having to limit this region by region at one time, because it does seem to be somewhat localized. Julia?
So, this is a really good presentation. And to comment and ask a question about the second point from your summary, when you're asking why go up bimodality and not just a random spread, it kind of reminds me of just kind of the theory of nonlinear dynamics and how the way that your nonlinear equation is set up, no matter what initial conditions you propose and the outcome, it'll always just kind of form some sort of some sort of trend or whatever. So Lorentz, butterfly effect or whatever. And so I'm wondering if the spreads that you were noticing were exclusively either a normal Gaussian or bimodal, or were you also noticing trimodal or multimodal in any cases?
So, yeah, I briefly looked at when I first started, how frequently does trimodal occur as well. And it's 5% or something like that. And so that was not frequent enough that I was I would expect that to become even worse with the limited sampling issue, because you have to be sensitive to all three of those rather than just two. And so I was that's kind of a dead end. But yeah, it's super interesting that it seems like there's this kind of preferential attraction to these two very different states.
Yeah, but it's really cool. I guess I'm curious, I may have missed it because I've been a few minutes late. How many years did you work over this?
I think it was 6 years. It's 550 forecasts.
So I'm curious if you have any thoughts about the impacts of different health connections in each of the years, Enso, La Nina, neutral, or negative for El Nino. Other health connections that might be caused by some of these patterns we've seen emerge, and if you're looking at the spread between years and saw any difference.
Yeah, so that's an interesting question. I haven't looked at does my bimodality more frequently occur in the El Nino regime versus La Nina or whatever. But in terms of the transitions between those really large-scale, long-lasting states being the cause for this, I think it goes back to, I think these events in which the bimodality is developing around have to be frequent enough, and the transitions between those states would have to be frequent enough to cause a lot of this. And so the transition from El Nino to La Nina, I don't think it occurs frequently enough for it to be, the cause for a lot of this. But maybe the bimodality does more frequently occur in El Nino years versus La Nina years, which I haven't explored yet, or whatever other large-scale variability patterns. But yeah, that's an interesting point. What's up?
So I was just trying to think broadly. It's very similar to the process. It reminds me of the bimodal Gaussian is sort of like a transit through a Lorentz butterfly. Just like a and so then I started thinking, why are there shoulders? Well, there's friction and photon exchange. Things can't get the other hand one way. Maybe on the other side, there's only a certain amount of sunlight, and the earth can only hold so much water. So there's shoulders on the whole thing. But why the dip in the middle? And I think Bonker got a really interesting example, and just intuitively, it seems might lie in really in just model parameterizations. Are they individually, if you perturb it one way in the middle, will it go to the right? If you perturb it one way in the middle, to the left, will it drift with other feedback variables leftward? And so if I don't know about this field, but my hunch is that there are modeling groups who have tried to publish papers about individual parameterizations and are they kind of unstable? Do they try to sort things, kind of split things? I don't know if that's the right way to think of it.
Yeah, so, I mean, I might have missed the question a bit, but yeah, I mean, I agree. I think it's, one of my points is, you know, what's creating this kind of like, that cutoff point that it seems like you're describing maybe of, you know, left to the phase space, you're getting this attraction towards the left-hand shoulder of the lens attractor, and then right to some cutoff point in the phase space as the model is initialized, it's being attracted to the right-hand shoulder. And I don't know the answer as to what that is, and you know, it probably varies from region to region. But yeah, it's an interesting point. And I think, yeah, what's that?
You gone and looked at the observations and seen what actually happens, and then look at what those model members that get the right mode correct versus what the wrong mode is saying?
No, so I haven't directly done validation to this, and it a big part of the study that we found is it's and I just didn't have enough time to include is evaluating this bimodality in like a rigorous skill scoring kind of idea where comparing it to the validation values. This non-Gaussian behavior like turns those traditional skill scoring metrics to like crap because it just isn't able to handle it. And so I think that's also another big finding to this study is some of those skill scoring metrics need to be revised if they're hoped to be useful in this context.
So do you think after 2 weeks of prediction time, it's useful not to use ensemble mean rather than having two ensemble means saying you are going one direction or the other?
Yeah, so, well, I would say yes. I think the problem to that is, you know, this KDE fit, for example, is far more expensive to do to a distribution than just a Gaussian fit. And so I think part of the hope of this, and maybe a future direction this would take, is, you know, identify, if we're able to identify where the bimodality is most likely to occur during some time, during some location, under these specific events, we say, okay, you need to start fitting KDEs to those distributions because it's important. But I don't think it's practical to do that for all forecast lead times over the entire globe, just because it's much more expensive to run than just fitting a Gaussian distribution.
All right, if there aren't any more questions, let's give them another round of applause.